Hello everyone, in this video we will solve problem number 2. It's quite interesting problem. So let us see. So we have a soil profile here at a site that consists of between 0 and -8, so we have sand, and then between 8 and 12, we have clay. And we are given the dry and saturated unit weight for each soil. We are given also K naught equals 0.5. K naught is the coefficient of earth pressure at rest, and it is the ratio between the effective horizontal stress and the effective vertical stress. And I underline the word effective. K naught is always applied to the effective stress. So the water table is initially at a depth of 1 meter below the surface. You can see the water table here, and it will be rapidly lowered to a depth of 6 meters and maintained at that level permanently. So I would have the groundwater level here. It will drop to -6 meters over, and this will be a permanent position for the groundwater table. The height of capillary rise in the sand is assumed to be 0. So this sand, when the water drops, it will not hold onto any suction, basically. Now consider 2 points in the soil profile. Point A at depth of 4 meters, so that's -4 meter. Ground surface is 0. This is -1 here, the groundwater level. And point B at depth of -10 meters. So if this sand thickness is 8 meters and the clay bottom elevation here is -12, so the point B is located in the middle of the clay. So now what's required? Determine the effective vertical and horizontal stresses at points A and B, point A and B. Initial conditions where the water table is 1 meter below the surface. So when the water level is here, we need to determine basically the effective vertical and horizontal stress at point A and B for the initial condition. And B, a long time after lowering the water table to 6 meters below the surface. So when the water level here is 6, and after a very long time, we are required to determine the effective stresses at point A, vertical and horizontal, and likewise at point B. Essential knowledge: we need to know the meaning of pore water pressure, effective stresses, and the total stress in the soil. And we have these equations which I covered in question number 1. So basically the total stress is the sum of the effective stress plus the pore water pressure. And this applies to the total to the general case, or also the overburden when we have the note, sigma V naught. You need to remember that the pore water pressure is basically, it's equal all round pressure in all directions. But for the earth pressure, the general case is when you have a vertical stress sigma V, that's different from sigma H. When this is effective values, the ratio between the lateral stress effective and the vertical stress effective, this ratio is K naught here, which is 0.5 for the sand and 0.3 for the clay. Solution strategy: basically we need to determine the total stress for pressure at any point under any condition, and then apply this equation here to determine the effective stress. Let's see how we gonna do this. So stresses before lowering the water level. So this is a ground condition, and we are now concerned with the groundwater table at -1. Point A, like I showed in problem 1, this is actually question 2, not question 1. It's written wrongly here. So basically point A, that's point A, it is carrying 1 meter of dry sand, because here the groundwater table is 1 meter below the ground surface, so the sand above here is dry, so it's carrying 1 meter of dry sand. Point A will feel this 1 meter of the dry sand, and the 3 meter of fully saturated sand. Why 3 meter? Because this is -1, this is -4, so I have here 3 meter of saturated sand. That's applicable to the total stress. But it also carries 3 meter of water, so above point A is basically a water column of 3 meter height. And we will use this to determine the stresses. So then, based on this important statement, and I strongly encourage you to write it for yourself. So sigma V naught, which is the total stress at point A, is basically the weight of everything above me in terms of soil. So I have 1 meter of dry sand. Dry unit weight is 16. Dry unit weight is 16 plus 3 meter. I have written it here for myself to make it easy. It's 3 meter time 19, which is the saturated unit weight of the sand. That's 73 kPa. I get U naught, which is the hydrostatic pressure at point A, is the water column above point A. It's 3 meter times the unit weight of the water. 3 meter, I have written it here to make it easy for myself. 29.4. So it would be straightforward now to determine sigma dash V naught, the difference between total stress and pore water pressure. Remember, pore water pressure is equal in all directions. So 73 take away 29.4, so I have 43.6 kPa. So this way I have determined the effective stress at point A. But the question also asks for the horizontal effective stress, because this is the vertical effective stress. The horizontal is basically K naught, which is given to us as 0.5 times sigma V dash V naught. This is not sigma H naught, that's sigma dash V naught. It's a typo here. So 43.6 times 0.5, that's 21.8 kPa. So I now calculated basically the stresses at point A. We repeat it for point B. For point B, let us see what point B is carrying. Point B carries 1 meter again of dry sand. It's carrying the full 7 meter of the saturated sand, which is the difference between the water level here -1, this is -8, that's 7 meter of fully saturated sand. And now point B, this is -10, this is -8, so 2 meter of saturated clay. Again, total stress. For the water, it is carrying 9 meter of water. Where does this 9 meter come from? The water level is -1. The elevation here is -10, so the difference is 9 meter. The rest is straightforward. So let us substitute. Sigma V naught is 1 meter dry sand, so 1 times 16, exactly like before, plus I have here 7 meter of fully saturated sand, 7 times 19, which is this thickness between the -8 and the -1, plus 2 meters of saturated clay, 2 meter of saturated clay times 20, 189 kPa. Likewise, U naught is pore water pressure, is the height of the water column, 9 meter times unit weight of water, 9.8, that's 88.2. So I would calculate the effective vertical effective stress, difference between the two, 189 minus 88.2, that's 108 kPa. I need to apply this equation similar to that, but remember again, this is sigma dash V naught, this is V naught. So I would apply it here, again this is V naught because it's typo, just copy and paste. I multiply 0.3, which is K naught of the clay here, given as 0.3, times 100.8, 32.2 kPa. Now I am done with the case before lowering the water level. I will repeat exactly the same for the case when the water level drops from -1 to -6. Let us do it. So this is a condition now. This is a groundwater table after lowering the water level. We will do exactly the same. And you need to be systematic here. Let us see what point A is carrying. Point A carries, in this case, I have 4 meters of dry sand because the problem says after long time or permanently. So after long time, the sand will be dry. So this sand here between level 0 and -6 will be dry because the water level was here at -1 and it dropped here to -6. This is -4 meters, so it's carrying 4 meters of dry sand. That's all point A is carrying. So now sigma V naught would be 4 times the dry 16. I don't have water here to calculate, so U naught is 0. This means that the vertical effective stress equals the total stress 64 because the pore water pressure is 0. For the lateral stress effective, I just apply the same formula. Again, the typo is actually has been carried forward through the problem. That sigma dash V naught is 0.5 times 64. That's 0.5 K naught of the sand times 64, which is the effective stress. I cannot stress enough that K naught is applied to the effective stresses. It is the ratio between the effective horizontal to the effective vertical stress within the soil. So that's 32 kPa. Let me repeat the same for point B. Point B, let us see what point B carries. Point B carries now 6 meters of dry sand, and then 2 meters of fully saturated sand between -6 and -8, and it's also carrying 2 meters of clay. That's when we talk total stress. It also carries 4 meters of water. Why 4 meters of water? Because now the water is at elevation -6, and this is elevation -10, so the difference is 4 meters of water pressure above point B. Substitute. Sigma V naught is 6 meters times unit weight of the sand. That's a dry sand, so I take the 16 plus 2 meters of fully saturated sand, this 2 meters here, so times 19, plus 2 for the clay, 2 times 20 for the clay, that's 174 kPa. Pore pressure, I have 4 meters, so 4 meters times 9.8, that's 39.2. Difference between sigma V naught and U naught will give me the vertical effective stress. 174, take away minus 30.2, that 134 kPa. Lateral stress, sigma K naught times sigma dash V naught, all effective. So I multiply the 0.3 because the 0.3 belonged to the clay, so times 134, that's 40.4. Let us have a look just to see the difference in the stresses between the first case and the second case. The first case when the pore water pressure was high, and the second case when the pore water pressure is low. So let us see. Point A before gave me this value. So compare that sigma dash V naught was 43.6, now it became 64. Likewise for the lateral stress effective. See point B. Point B, before it was the effective stress vertical was 100.8, now is 154.8. This is a good sign that our calculation is correct. Why? Because when you have a water level here that drops basically, so this should increase the effective stress on the soil, because when you have water, so the soil becomes buoyant, becomes submerged. As such, the weight that felt by any point within the soil would be less, given that the presence of the water makes things buoyant. So as you drop the water level, it means that the soil that was part of the soil that was originally carried by the water pressure is now carried entirely on the soil itself. So what you take from here is when you drop the water level, so expect the effective stress to drop. If everything else remain the same, like if the water level drops by say 1 meter, and the